Alright, so we're looking at lesson 30 today. We're looking at conservation of momentum. So hopefully after this lesson you'll understand some more about conservation of momentum. Whenever you have two objects that collide, the total kinetic energy after the collision is less than the total kinetic energy before the collision, because some of your collision is lost to sound and some is lost to heat. So if I clap my hands together, you hear some noise, that's some energy that's lost to sound, and your hands slightly get warmer when they collide. So some of your energy is lost to heat. Whenever you have two moving objects collide, the sum of the momenta after the collision is the same as the sum of the momenta before the collision if you have no outside forces acting on the system. This is true whether the amount of kinetic energy lost is big or small. Collisions where some of the kinetic energy is lost is called an inelastic collision, and so all real collisions are inelastic because they're all going to have some amount of sound and heat that are lost. However, we are going to look at totally elastic collisions, and that's where no kinetic energy is lost. Those are imaginary collisions. So we're looking at imaginary ones to make the math a little bit easier. If you go on into other physics classes, hopefully you'll get to look at some inelastic collisions that would be real life examples. So the law of conservation of momentum says if no external forces act on a closed system, the total momentum of the masses within the system will not change. So if we have a small mass and a big mass and apply the same force for the same length of time, the momentum changes of both masses have to be equal because the F delta T products are going to be equal. So small mass, big mass, same force for the same length of time, the momentum changes are equal. The formula we're going to be looking at for two masses in a head-on collision is this formula here. So mv plus mv equals mv plus mv. Mass and velocity of the first one before, mass and velocity of the second one before, mass and velocity of the first one after the collision equal plus the mass and velocity of the second one after the collision. So let's use that formula to do an example. 5 kilogram mass A and a 3 kilogram mass B are going to collide, and they want to know what is the velocity of the 5 kilogram mass after the collision. So we have a 5 kilogram mass with a velocity of 2 and a 3 kilogram mass with a velocity of -2. And it's negative because it's going in the opposite direction. After they collide, the 3 kilogram mass has a velocity of a +2. And we want to know what is the velocity of the 5 kilogram mass. So you're just going to solve your equation. So 10 minus 6 equals 5b plus 6. If you subtract, you'll get -2 equals 5b, and divide, you get the velocity is -0.4. And they only gave us one sig fig up here, so we have one sig fig in our answer. So meters per second is your units on velocity. Now we're going to look at a cannon and a projectile. What does it change in momentum of the system? Well, this is a closed system, so there is no change in momentum. So for this one, you would just put 0 for part A because there is no change in your momentum because we have a closed system. No outside forces are acting on this system. What is the rearward velocity of the cannon? So we're going to use the mass of the projectile times the velocity of the projectile is going to have to equal the negative of the mass of the cannon, the velocity of the cannon, because the cannon's going to be going backwards, so it has to be negative. So the mass, 0.02, and the velocity is 378, and then the mass is going to be, we're going to have 728, and we don't know the velocity of the cannon. So if you solve that, you get negative 0.010. And we have to have two sig figs because we have two sig figs in that number there. So meters per second are your units. For part C, what is the kinetic energy? So we're going to use our kinetic energy formula, which is 1/2 mv squared. So for the projectile, 1/2, the mass is 0.02, and the velocity is 378 squared. And if you plug that in, rounding to 2 sig figs, you're going to get 1400. And joules is your unit on kinetic energy. For the cannon, we're going to do 1/2. The mass is 728, and the velocity we just found was negative 0.01 squared. And then if you multiply, you get 0.036 joules. And again, you do 2 sig figs because we only had 2 from this number up here. And then the change in energy, there is no change in energy here because we can account for all of the change. We had two objects, so we have a kinetic energy of the projectile and the kinetic energy of the cannon, and then there is some energy that goes to the bang of the heat, and we don't know what that is. There's no way for us to figure it out, but there's no change of energy in the system. Okay, we're going to look at another example. We have a 1,000 kilogram car traveling east at a speed of 20 meters per second, and it collides at an intersection with a 3,000 kilogram truck traveling north at 10 meters per second. The vehicles stick together immediately on impact. So this one, we're going to have the mass and velocity of the car, and then the mass and velocity of the truck. And then the mass at the end is going to be the mass of the car plus the mass of the truck, and they're going to have the same velocity because they were stuck together. So this one's going to have to be worked a little bit differently because they're not going in opposite directions. They're coming and they're hitting at a right angle. So the mass of the car is 1,000. The velocity of the car is traveling at 20, and it's going to the right. So it's 20 at 0 degrees. The mass of the truck is 3,000, and the velocity of the truck is going at 90 degrees, so it's going to be 10 at 90 degrees. And then at the end, the mass is going to be a total of 4,000 because the mass of the car plus the truck adds up to 4,000, and we don't know the velocity at the end. So that's the first thing we have to do. Now on the left side, we can't just multiply those and add them together. We have to break them down into their vectors. And so this vector is 20,000 at 0 degrees, and then this one is 30,000 at 90 degrees. And so we're going to draw one vector and then the other vector. That's a 90-degree angle, so we have 20 and 30,000. And then we need to find the hypotenuse and the theta. So you should be able to do that completely by yourself now. And if you find your hypotenuse, you should get 36,055. And if you find your angle, you should get 56.31 degrees. And so that's what these two numbers add up to be. And then to find your velocity, you're just going to divide by 4,000. And so you only divide the 36,000 by the 4,000. The angle doesn't change. So you should have 9. And we only have 1 sig fig on all of these, so it's 9.01, but just 9 is 1 sig fig, and then 56.31 degrees is our velocity. And the units on velocity is meters per second. And so that would be your answer for that one. So you have to pay attention to the direction that they give you in the problem to make sure that you set it up correctly. But hopefully that helps you a little bit with lesson 30. Make sure you do 1 through 20 for homework and the curveball questions so we can go over any questions you have tomorrow.